day, guys. Welcome to this class. And in this class, we are going to be solving all the exercises that is involved in this electric field, right? So the first exercise here, we can call it exercise 2.1. In here, first exercise here, exercise 2.1. It says that an electron of charge E equal to 1.6 times 10 raised to the power 19 coulomb. Make sure you are writing it down if you don't have the textbook. Is situated in a uniform electric field of intensity or strength of, I told you that electric field can be given in volt per distance. So they gave us an electric field in volt meter here, which is 12,000 voltmeter, right? And they gave us the charge of the electron. They said that the charge of the electron is equal to 1.6 times 10 raised to power minus 19 coulomb. Find the force on it if its acceleration and time taken to travel 20 millimeter from rest. Are you getting it now? Yes. So it says find the acceleration. Say find the force. Find the force. That is question A. A says find the force. B says find the time it take to travel a distance of 20 millimeter. 20 millimeter. So time it take to travel a distance of 20 millimeter. We are going to be dissolving this in a while. And C says that find okay, this is C. Yes, this is C. This is C. Let me put it C. Then our B here is acceleration. So let's go. Remember that force is related to electric charge by QE, right? Yes. And Q, in this case, Q is same thing as E. That's the charge of the electron, right? Then the intensity has been given to us. So we just plug into this formula, that is F is equals to QE, that is 12,000, right, times 1.6 times 10 raised to the power minus 19. And anything you have there is the answer, that is 1.92 times 10 raised to the power minus 14 Newton. Are we together now? Yes. So number 2 is the time it will take. No, number 2 is the acceleration. Now, since we have gotten the force as 1.92 times 10 raised to the power minus 14, right? Recall that force is equal to MA. So A will now be equal to F over M. What is our F? 1.92 times 10 raised to the power minus 14. What is our A? What is our M? Our M is mass of the electron, right? So that is 9.11 times 10 raised to the power minus 31. So if you evaluate this, you will have an answer like 2.12 times 10 raised to the power 16 meter per second. What is our C? Our question C here says that the time it will take to travel a distance of 20 millimeter. Recall here that S is equal to UT plus 1 over 2 80 square, right? Yes. So x equals to ut plus 1 over 2 80 square. If we do this, it will lead us to a quadratic equation. But let's look for a simpler way we can use. Let's see if there's a simpler way we can use right now. What if we use v to be equal to u plus 18? Okay, there's no simpler way. Let's just use this. Because in this case, now it will require us to look for the velocity, and nothing was mentioned about the velocity. It's fine. So let's solve for this now. Our s is 20 millimeter. That's same thing as 0, right? That's 20 over 1000. So that's 0.02 equal to our ut. So they say it started from rest, right? Yes, it started from rest. So since it started from rest, what will happen? That means that this place will be equal to 0, right? Okay, nice. So it's not actually a quadratic equation. So this side will be off, so that become 1 over 2 times. We have gotten the acceleration here to be what? 2.12 times 10 raised to power 16, right? Yes, times t squared. So make t the solution formula. T will now be everything divided by 0.02 all over 1 over 2 times all in square root, right? Yes, so if we evaluate this, we'll have an answer like 1.37 times 10 raised to power minus 9 seconds. So let's go to exercise 2.3. Exercise 2.3. So exercise 2.3 says that what is the magnitude and direction of the electric field 2 cm away from a fixed charge? So it's like this, a fixed charge Q, right? And this Q is producing a field at this point 2 cm away, right? Okay, now they gave us the charge as Q to be equal to 3.0 times 10 raised to power minus 10 coulomb, right? So remember that E is equal to what? KQ over R square, right? So K is 9 times 10 raised to power 9 times what's our Q? Our Q is the charge as 3.0 times 10 raised to power minus 10, right? All over R square. So this cm converted to meter is 0.02 square. So when you press your calculator, anything you have is your final answer. I won't press it. You do the work yourself. So that's the answer there. To do that. Then, well, how do you get the direction? The direction is very easy. It's away. So this charge is bringing it out, right? It's producing it out away. So that is outward, right? Yeah. So the direction is outward. Now, option B Question B in this same 2.3 says that how far away from the point charge does the feed drop to 20% of its value? So in this case now we'll be forced to write the answer. So 20% drop to 20% of its value. So the answer we got is 6.8 times 10 raised to power 3. You can confirm it. If it's not the same with your own, then maybe I might make mistake or check well from your calculator. So 20%, right, times the feed 6.8 times 10 raised to power 3 will give you 20% times 6.8 times 10 raised to power 3 will give you 1360. So that means that they are indirectly asking you for distance kq over r square. Then make r solve it a formula. That means that r is equal to, right, the root of kq over e. What is k? 9 times 10 raised to power 9. What is q? 1.6 times 10 raised to power minus 19. What is e? What we just calculated for? 30.60. So when you press your calculator, anything you have there should be your answer, right? Yes, anything you have there should be your answer. Okay, that will be the answer. So the next question here is a neutral molecule. Listen to this question very carefully. I know most of you will be looking for the solution to this question. A neutral molecule, I get it now. Yes, a neutral molecule. A neutral molecule H2O in its vapor state has an electric dipole moment of 6.2. An electric dipole moment. I know most of you will say, but we did not talk about electric dipole moment. Don't worry. Those are the tricks that we'll be explaining on how to solve questions. We'll talk more about electric dipole moment in the coming chapters. But for now, let me show you the tricks of how to solve this. Right? It says, how far A says, how far apart are the molecule center of the positive and negative charge? Forget. He's just trying to talk about distance. So forget about the how far apart or how far apart. Just take it. We are looking for distance. This C here is what? Charge, right? Charge. Okay. And this M here is meter, that is distance. Is it not? M for meter, that is distance. And the symbol for charge is Q, right? And the symbol for distance is E. So sorry. The symbol for distance is, you can call it D or arrow, anyone. So I'll call it D. So it means that from here, QD is equal to, right? Is equal to dipole moment. So that's equals to 6.2 times 10 raised to power minus 30. Are you seeing the logic now? I just got the formula from this unit. All right. So now, what is Q? Q is the charge of an electron, right? So that is D will now be 6.2 times 10 raised to power minus 30 all over Q. That is 6.2 times 10 raised to power minus 30 all over Q is 1.6 times 10 raised to power minus 19. So if you press your calculator, we have an answer like 3.9, right? We have an answer like 0.9 times 10 raised to power minus 11 meter. That's the answer. So let's go to question 2. Question 2 here says that if the molecule, I get it now, yes, if the molecule here, if the molecule, question B here say that if the molecule are placed in an electric field of 1.5, what is the maximum torque exerted on it? Recall that torque is same thing as force times distance, right? Same as moment. And so, but force, we also know that distance can be arrow. We just choose in the previous option to be D. Same thing as arrow, so that is F times arrow, any one. But this F here is what? Is what? K, right? Q, sorry. Yes. But this F, in problem solving, you must think. I'm just solving it like this, not that I've written it before. This F is QE, is it not? Yes. F is QE. So if we substitute, that becomes our torque. Our torque will now be QE times R. Is it not? Yes, that's it. So from here it becomes easy. We can just substitute directly, right? Because we have gotten our distance before. So our QE here, our Q here is charge of an electron 1.6 times 10 raised to power minus 19 times the electric field given to us is 1.5 times 10 raised to power 4, and the distance given to us was what we calculated for, that's 3.9 times 10 raised to power minus 11. So when you press your calculator in this now, what should you have? When you press your calculator in this now, I get it, times 1.5 times 10 raised to power 4 times 3.9 times 10 raised to power minus 11. You should be able to have 9.36, right? That's 9.36 times 10 raised to power minus 26. That is Newton meter. Alright, see, this is very easy. The last exercise I will give you as solution, as your exercise to solve, and I will give you the tips. It says, what is the magnitude of a point charge whose electric field is 50 cm away and has, okay, the electric field is 50 cm away and the electric field is 2.0 Newton per coulomb. That's very easy, right? Because they gave you the distance, that is, they gave you distance to be, they gave you arrow to be 50 cm, and they gave you the field to be 2.0 Newton cm. Are you getting it now? So what you should do here is that use E to be equal to, right, KQ over R square. So you make Q the subject of formula. Q will now be equal to ER square over K. Then you substitute this, your E, your R, then your K is 9.0 times 10 to the power minus, sorry, times 10 to the power 9. You already know those values. Alright, thank you very much. God bless you. We see on chapter 3. Our next chapter is chapter 3. That's Gauss law. Make sure you like, subscribe, and share. God bless.